In this video, let us discuss about state transition matrix and its properties. The state transition matrix relates the state of the system at t is equal to t0 to its state at a subsequent time t when the input is 0. Actually, if the system is having some initial conditions, then it will produce an output. Since this output is present even in absence of an input, it is called as a zero input response, because here we have written that input is equal to 0. So there is an output even in absence of an input. It is called as a zero input response, and mathematically we can write it as x ZIR, that is zero input response of t, is equal to e raised to at into x of 0, that is equal to inverse Laplace transform of Si minus A inverse into x of 0. Let us derive this expression. So in order to define the state transition matrix of a system, here we have defined the state transition matrix, but now we will derive the mathematical expression for the same. Let us consider the state equation, that is x dot is equal to ax plus bu. So here, as we already know, x is a state variable and u is an input. So while defining the state transition matrix, what we have assumed is u is equal to 0, that is input is equal to 0. So if input is 0, the above equation will become x dot is equal to a into x. Now let us take the Laplace transform on both sides of this equation. Let us take the Laplace transform on both sides. So if we take the Laplace transform on both sides of the above equation, the equation will become, here we are considering the initial conditions. So while taking the Laplace transform, you need to consider the initial conditions. As I already told, x dot is nothing but differentiating x with respect to t, that is dx by dt. Its Laplace transform is x of s minus x of 0, where x of 0 is the initial condition. This is equal to, and Laplace transform of x here, that is x of t, is a into x of s. So let me take this a into x of s on this side. So this will become s into x of s minus a into x of s, that is equal to x of 0, So this is equal to x of 0. Now here we can take x of s common. If we take x of s as common, the term inside the bracket will be, this will be Si minus A. Okay, this is equal to x of 0. x of 0, x of 0. So let me write the expression for x of s. So x of s will become, so I will write here x of s is equal to, so this si minus a, it will become inverse si minus a inverse, si minus a inverse, si minus a inverse, okay, si minus a inverse into x of 0, into x of 0. So now what we'll do is we will take inverse Laplace transform on both sides. So taking inverse Laplace transform on both sides of the above equation. So inverse Laplace transform of x of s is x of t. Okay, this is equal to, I will write inverse Laplace transform of inside the bracket si minus a inverse, si minus a inverse into x of 0. This is si minus a inverse into x of 0. X of 0. Okay. Now what we'll do is, let us compare this equation. Let us compare this equation with x of t is equal to phi of t into x of 0. So here the coefficient of x of 0 is nothing but phi of t, which is inverse Laplace transform of si minus a inverse. So here phi of t is nothing but, it is inverse Laplace transform of si minus a inverse, si minus a inverse. Si minus a inverse. So this phi of t is nothing but a state transition matrix, which is also written as, this is equal to e raised to capital A into t. Okay, so where this x of t is nothing but, state of the system, at a time t. X of t is a state of a system at a time t, and x of 0, this is a state of a system at a time t is equal to 0. And as I told, this phi of t is a state transition matrix, and it is also written as e raised to a into t. Okay, so where a, we have already seen, it is a system matrix. So let us see the properties of a state transition matrix. we have defined the equation for the state transition matrix as phi of t is equal to e raised to at, which is equal to inverse Laplace transform of Si minus A inverse. The first property is phi of 0 is equal to I. So how this is equal to I is, see, this is the equation for a state transition matrix, that is phi of t is equal to e raised to a into t. This is the equation. Now let us put t is equal to 0. If we put t is equal to 0, then phi of 0 will be equal to e raised to 0, which is equal to 1. So that is nothing but an identity matrix or the unit matrix. This is how we have proved the first property of a state transition matrix, that is phi of 0 is equal to I. So the remaining properties, will see the proofs of remaining properties in the next video. Thank you.